Hello everyone, welcome to this video on Uart protocol, design and verification in UVM. I am Kundan Gupta and in this video we will explore Uart from its basic concept all the way to how it is verified using Universal Verification Methodology or UVM. Here is what we will cover in this session. A short introduction to UART, then we will see data framing in UART, the block diagram and its various signals like transmitter, receiver and clock generator. Then we will see how UART communication happens between transmitter and receiver. Then we will see design of UART and finally verification of UART in UVM. By the end of this video, we will understand not only how Uart works but also how to verify it effectively in UVM based Testbench. So what is Uart? Uart stands for Universal Asynchronous Receiver and Transmitter. It is asynchronous because receiver and transmitter does not share any common clock. UART is basically a hardware communication protocol used for serial communication between two devices. Their devices may be microcontroller, sensor or computers. It exchanges data bit by bit over only two wires. One is for transmitting and one is for receiving. Here is the block diagram. We can see it has two wires. One is for transmitting and one is for receiving. It communicates between two devices just by using these simple two wires. Next, let's see about data framing, which defines how a single byte of data is structured before transmission. A UART frame usually includes a start bit, data bits, parity bit, and stop bits. A start bit is always 0 and it indicates the beginning of the transmission. Then comes data bits, which is 5 to 9 bits, but commonly it is 8 bits, and in this LSB is sent first. Then comes the parity bit, which is optional and it may be even, odd or none. Then a stop bit came and it indicates the end of the frame. A stop bit may be 1 or 2 bits. This framing ensures the receiver correctly identifies where each byte starts and ends. Are the component of a UART data frame. First is ideal state. The line is held at logic high state. Then when data bit comes, the transition from high to low occur. It indicates the start of the data frame. Then the data bits comes, which is 5 to 9 bits but mostly 7 to 8 bits. It's transmitted after start bit and they are usually sent in LSB order. Then the parity bit, which is optional, is sent and it is used for error detection. Then a stop bits comes. A stop bits may be 1 or 2 bits at the end of the frame, which is logic high. This is how the data frame of UART looks like. Here is how data frame look like. First the line is set to idle. Then a start bit comes, which is 0, logically 0. Then our data bits comes. Then parity bits comes, which is optional. Parity bit may be even, odd or none. Then a stop bit comes, which is logically high and it indicates the end of the data frame. That means the receiver successfully received the data bits. Here is how the framing works step by step. The CPU sends the parallel data to the UART. Then UART adds its framing bits, that is start, optional parity and stop bits, to create a data packet or frame. Then it sends the packet serially bit by bit across the line. Then the receiving side of UART reads the bits one by one and after removing the framing bits, that is start, optional parity and stop bits, it converts the data back into parallel form to send to its internal data bus. Now baud rate. Baud rate is simply the number of bits transmitted per second. For example, the baud rate is 9600. It means that 9600 bits per second. If baud rate is 115200 baud, then it means 115200 bits per second. Since UART is asynchronous, so both devices must use the same baud to stay in sync. For example, if the baud rate is 9600, then each bit duration will be 1 upon 9600, that is 104.16 microsecond. Now both devices know that each bit is hold for 104 microseconds. Now let's see an example. Suppose we have clock frequency of 50 MHz and baud rate is 9600. Then our TX clock count is calculated as frequency of clock upon baud rate, that is 50 into 10 to the power 6 upon 9600, that will be 5208. For TX clock we need to take half of this, that is 2604. Now the question arises, why we are taking half of this? We are taking half of this because we have to toggle the clock, and in one half it will be 2604 and another half it will be again 2604, then total it will become 5208. Now in the receiver side we are oversampling the clock. We can oversample it as many times as we like, but typically it is oversampled 16 times. To get the accurate data, we are oversampling the bits to get the accurate data, that it is logically high or logically low, that is 1 or 0. So for RX clock, we calculate TX clock upon 16, that is 5208 upon 16, that will be 325. Here is the diagram of oversampling in the receiver side. Each bit is oversampled 16 times and we are taking middle value of each bit. Here also you can see each bit is sampled 16 times and we take the middle value of each bit. Why we are taking middle value? To get the accurate data, that is it is 1 or 0. Now let's move to the design of Uart. The design of Uart basically contains 3 modules: clock generator, transmitter and receiver. Clock generator contains 3 signals, 3 input signals, that is baud, frequency of clock, reset, and its output is RX clock and TX clock. The formula for calculating RX clock and TX clock we have seen earlier. Okay, now move to the Uart transmitter. Here are the input signals of the Uart transmitter, that is TX clock which we are receiving from the clock generator. Here the TX clock, it goes to the Uart transmitter, then reset, then TX start, which indicate that we have to start sending the data. Here is the actual bits that we are sending to the receiver. Here is the length. Length indicates what length of the bit should be. It should be 5, 6, 7, 8. Which length of bit we are sending to the receiver. Then comes to the parity enable. Parity enable tells us that whether the parity is optional or not. If it is not optional, then parity enable is 1. Then comes the parity type. Parity type is even or odd according to our choice. Then stop to. Here stop to because there might be 2 stop. If a stop to is high, it means there will be 2 stop, and if stop to is 0, it means there is only 1 stop. Now in the output signals, there is TX error and there is TX turn. Now this TX is connected to RX of the receiver. I will explain in the next slide. At last we have Uart receiver. Now for Uart receiver, here are the input signals. First is RX clock. This RX clock we are receiving from the clock generator. Then reset, then RX start. RX start indicates that now we are ready to receive the bits, and then comes to RX. Now this RX is connected to the TX of the transmitter. From this line only the bits are sent from the transmitter to the receiver. Then comes the length. The length we are expecting that is sent from the transmitter. Now the parity enables. Parity type, which type of parity it is even or odd. Then the same stop to, which we are indicating here, transmitter. Stop to indicate that there is 1 stop or 2 stop. Now the output of the receiver is RX out, RX error and RX done. If RX1 will be high when our parity type mismatch, and RX done will be high when we receive all the data correctly, and RX out store the incoming data. Now let's see how the 3 modules of Uart connected to each other. The first block is clock generator, whose input is baud rate, frequency of clock and reset, and whose outputs are RX clock and TX clock. The RX clock is connected to the receiver of Uart, and the TX clock is connected to the clock of the transmitter of Uart. Now the transmitter will produce the TX data, and this TX data is connected to RX of the receiver Uart. So the data we transfer from TX data, the same data we will receive from the transmitter of the RX out. Then if both are same, it means we successfully pass the data. If the data is different, it means the data might be corrupted. Let's see the FSM of the transmitter. Transmitter define following of 7 states. First is idle, second one is start bit, third one is send data, then send parity, send first stop, send second stop, and lastly done. In idle, it is waiting for the transmit request. Then a start bit comes. When start bit comes, it goes to low level, then send data, then in which we transmit the data bits, in which LSB is sent first, then we send the parity bit, then we send the first stop bit, and if stop 2 is enabled, then we send the second stop bit, it is optional, and then last we send the done, which indicate our completion of the transmission. Next is FSM of receiver. FSM of receiver also have 7 states. The first one is idle, then start bit, then receive data, check parity, check first stop, check second stop, and done. The idle default value is 1, and when it goes low, it means the start bit comes. Then after the start bit, we start receiving the data bits, and then we check the parity, which is optional. If parity enable is high, then only we check the parity bit. Then we check, receive and check the first stop bit. Stop bit is always high. Then we check the second stop bit. If the stop 2 is high, then only we check the second stop bit, which is also high. Then finally done signal, which indicate completion of the reception. So now let us start our UART design code. Now we have understood how UART clock work theoretically. Let's move on the design code implementation of UART. We will discuss each part, the clock generator, transmitter, receiver, and finally how everything is connected together in the top module. We will start with the clock generator module. The UART transmitter and receiver works at different clock frequencies. The transmitter sends beat at baud rate, while the receiver needs to sample each beat multiple times for accurate detection. That's why we need to create two derived clocks, TX clock and RX clock, for a higher frequency input clock. Let's look at how that code is implemented in EDF diagram. Inside the clock generator, we have declared input as clock, reset, baud, and output as TX clock and RX clock. We first declare the internal integer, counter, and maximum count values. RX max, TX max, which is initialized to 0, and RX count, TX count, which is also initialized to 0. Now TX max defines how many system clock cycles make up one transistor clock period, and RX max is smaller since receiver clock runs faster for oversampling. And RX count and TX count is used to count the number of clock period that we need to toggle. Inside the always block, we assign the value of TX max and RX max. There is a case statement inside the always block, and all possible value for the baud rate is declared, and calculation for RX max and TX max is calculated and declared here. Calculation is calculated by using the formula. For TX max, it is calculated as frequency of clock upon baud, and for RX max, it is calculated as TX max upon 60. So if reset comes, then we assign TX max and RX max to 0. Else, if some baud comes, then we assign TX max and RX max value correspondingly. Then in the next always block, we have declared the logic for the count value. See here, I have declared two always block for TX clock and RX clock. For TX clock, if reset will come, then we assign RX max to 0, TX counts to 0, and RX clock to 0. Now, RX count is less than RX max, then we increment the count value. If it is not equal to, then in else part, if it is greater, it means if it is greater than the RX count, then we toggle the clock and we again make the RX count to 0. Similarly, for TX clock also, if reset will come, we assign TX max to 0, count to 0, and clock to 0. And if reset is not, then if TX count is less than TX max, then we make TX count to TX count plus 1. That is, we are incrementing count value of transmitter clock. If TX count is greater than TX max, then we toggle the clock and make TX count to 0. Now, this is the logic for our clock generator. Now we will see how UART transmitter works. Let's move to the transmitter design, the module that sends data serially. At the top, we define the TX clock, TX start, reset, TX data, length, and configure signals for parity and stopping. and output as TX, TX done and TX error, where TX represents the serial output line, TX done indicates transmission completion, and TX error represents for any internal error. We have also declared TX range where we store the parallel incoming data and start bit as 0, stop bit as 1, parity bit as 0 and count as 0. Internally we have defined a finite state machine, that is FSM, using 7 states. So which state we are using? First is idle, then start bit, send data, send parity, send first stop, send second stop, and finally done. And we have combined all together in type diagram, which is represented as state type. Now we have declared two states, that is state and next state. And initially both are idle. The FSM transition follow the Uart transmission steps. Here idle, it is always logic high, waiting for TX start. Then start bit derives line to 0. Then send data, sends bit LSB first. Then send parity comes. It is optional error bit. If enable, then we send the parity bit. Then there are two stop bits. If both bits are enabled, then we send two stop bit. If one bit is enabled, then we send one stop bit only. Then last is done, which means transmission complete. Next, I have written the logic for the parity generator. If parity is enabled, then parity bit is sent. Now parity bit can be two types, odd or even. If parity bit is 1, then I have considered it to be odd. I have written a case for including the different type of lengths. If length is 5, 6, 7 or 8, there are different cases. Now for odd parity, we simply have to join all the bits. And for even parity, we have to take the XOR of all the bits. By using this logic, we can calculate the parity generator. Next is the logic for the reset detector. If reset is high, then state is set to idle. If there is no reset, then state will be next state. There is FSM next state logic, which decide what happens at each clock. So we begin. I have written the case state. There are 7 states total, starting from idle, begin and end. I have first declared TX to be 0, TX to be 1, because in idle case, TX is always set to be 1. And if 0 comes, it means now start bit comes and then send data. Okay, then I declare TX raised to be 0. All the 8 bits are declared or initialized as 0. Then TX error is 0. If TX start is 1, that means we have to move to the next state, that is start bit. And if TX state is not high, the next state will be idle only. Then we move to the next state, that is start bit. Here also we begin and end. Here we load the TX data to the TX array, and in TX line we send the start bit, and next state will be send data. Then in send data logic we begin and end, and we have declared count. The count logic is written in another always block. I will explain later. Yes, if count is less than length minus 1, length the number of bits we are expected to send. If it is less than 1, then next state will be send data only, and we pass the data to the TX line from the TX range. And if count will be greater than less minus 1, and if parity is enabled, then TX is sent the last bit value, and next state is send parity. If count is greater than length minus 1, and if parity is not enabled, then we send the last bit value to the TX line, and next state is send first stop. Then the next state is send parity if it is enabled. In parity bit, in send parity state, we pass the parity bit to the TX line, and next state is send first stop. Then in the send first stop state, we begin and end. We send our stop bit, that is here I have written stop bit. I have declared stop bit is always 1. So in stop bit, TX is send. If stop 2 is enabled, then the next state will be send second stop. Else next state will be done. Now in second stop, send second stop state, we pass second stop bit to the TX, that is 1, and next state will be done. In done state, the TX done is set to be high, and next state will be idle. And by default, the next state is idle. Then we end the case and end here. Next is the count logic. I have written in separate always block for transmitter. Count, it counts the number of bit sends to the receiver side, that is TX line. So in initial state count is 0, in started state it is also count is equals to 0. In send data we are sending actual bit, so we are incrementing count to count plus 1, and in all case count will remain 0 and default also count is 0. So we end case here and we end the module of our transmitter. Come to the receiver side, which does the opposite to the transmitter. It receives serial bits from the line, reconstruct them into parallel data and check for the errors. So here are the inputs: RX clock, RX start, reset, RX line. Through this line the data will come from TX, and there is length which indicate which length of bits need to receive, and parity type parity enable, stop to, and output are RX out, RX done, and RX error. RX out is the received byte, RX done reception completion, and RX error indicate parity or framing errors. Next, I declare the parity as 0. Data read is initialized to 0, and there is to count and bit count, which is also initialized to 0. Now count will count the number of clock tick. In receiver side we are receiving the received bit and we are oversampling it 16 times. So this count will count the 16 times, and this bit count count the actual bit received. I will explain it in the code. Like transmitter, the receiver also use 7 state FSM: idle, start bit, receive data, check parity, check first stop, and check second stop, done, which is written in type def enum, and its name is state type. Now idle wait for the start bit. The start bit confirms where it start after oversampling. Receive data reads the data bits and it reads the LSB first. Check parity will verify parity bit is enabled or not, and check first stop will validate 1 or 2 stop bits, and then finally done, which is used to indicate the completion, and it set the RX state to be 1. Now a state type is of two types: a state which is idle and next state which is also idle. I first declared both to be idle. To the state logic, first is reset detector. If reset will come, then a state will be idle, else a state is set to be next state. Now next state decoder and output. First, I have written all the state in the case statement. First is idle. If idle will come, then RX data and RX error is set to 0. And if RX data is 1 and not RX, it means a start bit comes. Then next state is set to start bit, else next state will remain same as idle. Now in the next state is start bit. If count equal to 7 and RX is equal to 1, the next state will be idle. And if count is equal to 15, then next state will be receive data, else next state is start bit only. Now the oversampling uses count. For every receive bit, the line is sampled 16 times per bit period. At the middle sample count equal to 7, the bit is last as valid. That's why we are taking value at count equal to 7. Next move to the next state, that is receive data state. If count is equal to 7, that means we reach to the middle of the 16 sampled clock. Then we set the data to data read value. We capture the data and set it in the data read value. Else if count is equal to 15 and bit count is equal to length minus 1, it means that we have successfully received all the bits. Then I have written a case statement. In case statement, if the received bit is a 5 bit, 6 bit, 7 bit or 8 bit, RX out is declared from read data. If the bit length is a 5, then we capture the data from the data read from 7 to 3. If it is of 6, then we capture the data from the data read from 7 to 2, similarly for 7 and 8. For error checking, we are computing the parity bit. If parity bit is 1, then parity is XOR of all the data read, and if parity bit is 0, then XOR of all the data read. If parity is enabled, the next state will be check parity. If parity bit is not enabled, then the next state will be check first stop. Else next state will be receive data. That means in this case only, in this state only. This else is coming from here, if, else if, and else. Check parity state. In check parity state, we are comparing the received parity and the calculated parity. Now if it is to the middle value, we are checking the receive parity and the calculator parity. If both are equal, then Rx error is set to be 0, else Rx error is set to be 1. Else if count is equal to 15, then we move to the check first stop state. Else we remain in the same state, which is check parity, which means if count is not equal to 15. Now in check first stop state, if count is equal to 7, that means we reach to the middle value. If Rx is not equal to 1, it means error is equal to 1. And if Rx is equal to 1, then means there is no error and Rx error is set to be 0. Else if count equal to 15, and if stop 2 is enabled, then we check the second stop bit. Else next state will be done. Now move to the check second stop state. If count equal to 7, here also we check Rx is not equal to 1, that means error occur, and if Rx is equal to 1, it means error does not occur. Else if count equal to 15, then next state is done state. Here Rx error check the stop bit. The stop bit is always set to be 1, and if it is not 1, it means error has occurred. Simple. Now in the done state, we set Rx done to be high, next state is set to be idle, and Rx error to be 0. The receiver count logic, for which I have written the separate always block and case statement for the different states. First is idle state. In idle state, both count and bit count is set to 0. Then start bit state, if count is less than 15, then we increment the count, else count is set to be 0. In receiver state, if count is less than 15, we increment the count, else count is 0 and bit count is bit count plus 1. In check parity state, if count is less than 15, then we increment the count, else count is set to be 0. Similar for the check first stop, if count is less than 15, we increment the count, else count is set to be 0. And for check second stop also, if count is less than 15, we increment the count, else count is set to be 0. Then in done state, count is set to 0 and bit count set to 0. Then we end the case and end the module. It means our module completed. The next module is Uart module. Uart module connect everything: the clock generator, transmitter, and receiver. And here how it is wired, everything. In Uart top module, we take all the inputs and output, and then we connect everything with their respective module, such as clock generator, Uart transmitter, and Uart receiver. Finally, we have declared interface of Uart. This makes it easy to connect the DUT with UVM components like driver, monitor, and scoreboard. In UVM, for example, instead of connecting dozens of individual signals, we simply pass this interface handle. It is clean, organized, and scalable to handle the signals. So here are the different logic for the signals, and finally we end the interface. So it completes our design part of our Uart. So to summarize, the clock generator here, the clock generator create the proper timing signals, the transmitter convert parallel data to the serial form, and the receiver reconstruct back, ensure parity and stop bits are corrected, and finally the top module ties them together and interface make verification easy EVM. This entire code is fully synthesizable, modular, and easy to integrate with EVM based verification environments. Next, we will see the verification in UVM. Now that our Uart design is completed, let's move on the verification part, where we will test whether the design behaves exactly as expected under different conditions. For that, we use a very powerful and a standardized verification framework called UVM. UVM stands for Universal Verification Methodology. UVM is a system Verilog based verification methodology that provides a structured and reusable way to verify complex design. Instead of writing random test benches for every project, UVM gives us a universal architecture so that once we understand it, we can apply the same structure for any design. So UVM test bench consists of the several components we can see here, and these components work together in a layered fashion. Let's take a look on the UVM architecture diagram here. So first we will see the different component of the architecture. It starts from the sequence. Now sequence generates and sends a series of stimulus transactions. The sequence is like a pattern generator. It can create both randomized or the direct stimulus. For example, the different byte to sends through the Uart, different baud rates, parity modes, or a stop bit configuration. These transactions are then sent to the sequencer. Now sequencer just act like a traffic controller. It schedules and manages the flow of the transition between the multiple sequence and the driver. Now next comes the driver. Driver convert the sequence transaction into the pin labeled duty signals. Next is the monitor. Monitor absorb the duty signals and convert them back into the transaction. Next comes the agent. Agent group together the related component such as sequencer, driver and monitor in a single interface. We can see here agent. In agent there is sequencer, driver and monitor which are grouped together. Next component is a scoreboard. A scoreboard is used for checking. It compares the expected output and the actual output and tells us the correctness of our duty, whether our duty is passed or the failed. Next is environment. Environment integrates multiple components such as the scoreboard, agent and the coverage component. We can see here environment consists of the scoreboard and checkers and agent. Next is the test component. It is the top level component that configures the environment and the start sequences. Then configuration database. It passes the parameter and handles the connectivity among component. It is just act like a database. We store here our interface or some variable which is globally used. Next comes the factory. It is not a part of architecture, but I have explained its terms. It creates UVM component and enables the override dynamically. If we want to override, then at runtime, then we should use the factory. Next is the TLM port, which is used for the connection or communication between two components using port and input. So from here we can see agent consists of sequencer, driver and monitor. Sequencer and driver are connected by the TLM ports. Now driver drives the input signals to the interface. The interface is connected to the DUT. Now interface will send data to the monitor using TLM ports only. So to summarize the UVM architecture, here the sequences generates the stimulus. Sequencer controls the flow of sequence to the driver. Here sequencer and driver are connected via TLM ports. This driver sends data to the interface. Monitor absorbs the output and it sends the data to the scoreboard. The monitor and scoreboard are connected via TLM ports. Now the sequencer, driver and monitor are grouped together in agent. The scoreboard and agents are grouped together in environment. This environment and sequences are grouped together in top module. This is how our UVM architecture looks like. Now that we have understood the UVM architecture, let's go step by step through the Uart verification code in UVM. This code implements the complete verification environment including sequences, driver, monitor, scoreboard, agent, environment and test class for our Uart design that we have discussed. So here is #include UVM macros.sh and import UVM package. It is because we are including our library files. Then I have written the configuration class. This class extends the UVM object and it is used to control the behavior of our agent. Here we have used UVM passive and active. Enum is active is equal to UVM active. This tells whether the agent will be active or passive. Active means with only driver or sequencer. Passive means with monitor. In our Uart Testbench, we are using active mode, so the agent will generate and derive stimulus. This configuration class is a small but essential piece. It makes environment flexible and reusable. Then comes the different scenarios which we are testing. These are random baud one stop. This is our first scenario. Then we are taking random length with one stop. Then length 5 with parity bit, length 6 with parity bit, length 7 with parity bit, length 8 with parity bit. Then length 5 without parity bit. Similarly for 6, 7, 8. And we are taking rand baud to stop, rand length to stop. So these are the different scenarios which we will cover. And for these scenarios, there will be different class for each of them. So I will explain it in detail. Next comes the transaction class, which represents a single Uart operation. It extends from UVM sequence items, making it suitable for sequences and the driver. Inside this class, we have defined all the fields like TX data, baud, length, parity neighbor, parity data, stop to, and output like RX out, TX done, RX done, TX error, RX error. And also we have constraint for baud and length. The baud must be inside this value and length must be inside this value. Now here is the constructor for the transaction class. Now next we will discuss each sequence in detail. Let's move to the sequences which generate test case for our duty. We have created multiple sequence class for different test scenarios. For example, here is our first sequence class. with random bot and with one stop. So for creating sequence, we have to first declare a class randbot, then we extend it from the UVM sequence, and we have registered it to UVM object utils with our class name. Then we instantiate a transaction object, then we call our constructor, then we are calling for 5 times. Each sequence is calling for 5 times. In the virtual task body, in this task, we declare all our signals. For example, here we create a transaction, then we start items and finish items. After that, we assert tr.randomize, then tr operation, that is which sequence we are calculating. Length will be 8, baud rate will be 9600, reset will be 0, tx start will be 1, rx start will be 1, parity is enabled. Since we are only sending one stop, so stop 2 will be 0, and this is our first sequence. Let's move to the next sequence. In this sequence, we are randomly generating bot with 2 stops. So here also I made a class with name randbot with stop. It stands from UVM sequence, then register to the factory, then object of transaction, then constructor of the class. Then in task body, we repeat for 5 times, begin and end. In this, we have created a transaction, a start item and finish item. Then we randomize the transaction. Then tr top is randbot with 2 stop, reset will be 0, length will be 8, tx start is initialized to 1, rx start is 1, parity is enabled here, and stop it is also enabled. This complete the sequence with random bot with 2 stop. Next transaction class is of length 5 without parity bit. Similarly, for this transaction also we made a class, then register to factory, then declare a transaction tr, we call the constructor, then in task virtual task body, we repeat for 5 times, we declare the transaction class, start item and finish item, then assert tr.randomize and declare all our signals. Tr top, tr operation to length 5 without parity. This is our sequence. Then reset to 0, then we send data, then length is 5, tx start is 1, rx start is 1, parity is enabled, and stop 2 is 0, means there is only one stop bit. Next, our next transaction is length with 6 with parity. Similarly, we do for this also, then for length with 7 with parity, then length with 8 parity, length 8 with parity, and length 5 without parity. In length 5 without parity, we make parity enabled to 0. All the logic will be same. Similarly, for length 6 without parity, we make here parity enabled to 0. Length 7 without parity, we make here parity enabled to 0, and length 8 without parity, here also we make our parity enabled to 0. All the logic will be same, only sum of the signals changes from here. So whatever condition we are putting, we have to make that condition enable or disable in the TR signals. The next class is our driver class. Now driver is the active component which drives signals to the DUT. We extend driver class from the UVM driver, then we register it to the factory. Then in the build phase, we are accessing the virtual interface from the UVM config DB. Then we are using the reset. In reset task, we initialize all signal to 0 and reset to 1. And we also pass UVM info that system reset has done. System reset start of simulation. And we wait for the positive edge of clock. Then in the derived task, we continuously wait for the new transaction from the sequencer using sequence item port get next item PR. Then we derive all the input signal using the transaction field like tx data, baud, length, etc. Then we wait for the tx done to be high and rx done to be high from the DUT. And finally, we call sequence item port item done. Then we end the task and end the class. The driver also prints all the test information using the UVM info message. Here, UVM info message is used to print all the test information. Next class is our monitor class, which we extend from the UVM monitor. Monitor is a passive component that observes the signal from the DUT and reports them. Here we register our monitor class to the factory. We are using analysis port. We have drive, transaction and the virtual interface. then using the constructor class. Then in build phase, we are declaring the transaction, then send is the analysis port. We name the analysis port to be send. We are initializing it in the build phase, and virtual interface we are accessing it from the UVM config DB. Then in the run phase, we wait for the positive clock edge, and if reset will come, then we set reset to be high. Then we are sending to scoreboard by all the transaction by applying send.write TR. If not reset, then we assign all the value from the virtual interface to the transaction, and we put the transaction value into the analysis port and send it to the scoreboard using the command send.write TR, and we end the task and end class. Next, we will move to the scoreboard. The scoreboard is where the real checking happens. The scoreboard is extends from the UVM scoreboard. We then register it to our factory. We name our scoreboard as SCO. Then we are using analysis implementation port for receiving data from the monitor. We initialize our array to 0, address to 0, and data rate to 0. Then we are calling the constructor function. Then in build phase, we are initializing our UVM analysis implementation. Then in the virtual function void write, we are actually checking our TX data and the RX out. TX data, what was said, and RX out is what was received. If it is reset and it is 1, it gives the message system reset. If TX data is equal to RX out, it means test pass. And if it is not equal, it means test fail. So this completes our UVM scoreboard code. Next is the agent class. The agent class group together the sequencer, driver, and monitor. First, I have extended agent class from UVM agent, then register it to factory. Then I have called the constructor class. Then derive 3 classes, that is driver, UVM sequencer, monitor. In the build phase, we are calling both. If CFG is active is equal to UVM active, then we build both driver and sequencer. Else, otherwise we are only using monitor. In the connect phase, we connect the driver with sequencer. You can see here we are using TLM port for connection. And the next class is environment class. Environment class is the container for all the major components like agent and scoreboard. We extend environment from UVM env, and then we register it to factory, and then we call our constructor. Now UVM environment contains 2 classes, agent and scoreboard. So in build phase, I call both agent and scoreboard. And in connect phase, we connect monitor with a scoreboard using the TLM port. This ensures that whatever the monitor observes, the scoreboard immediately receives and checks. So the environment integrates all the lower level component into the working verification system. Finally, we have test class, which controls the entire verification process. It extends from the UVM test and builds environment and all other sequence type like RAN board with stop bits, RAN board length 5 with parity, and so on. In the run phase, we call the whatever sequence we want to run. For example, here we call RAN 81 WOP, which means RAN board of length 8. Here we are running the random board 8-bit without parity sequence. This test can easily be modified to start any other sequences. Just one line change. If we change this line and put any other sequence, it will run that sequence. So here we raise the objection and drop the objection to run this. And the next is our module class. Finally, at the very top, we have our Testbench module. In the Testbench module, we instantiate Uart interface and Uart top DUT, which connect all the signals. We also generate our clock, then set up our interface handle for the UVM. Then we call dump file and dump bars to add the waveform generation. So this is the complete simulation setup. Once we run this code, UVM automatically builds the entire hierarchy, execute the test, and display the UVM data flow and verification log in our script. This UVM test bench verifies every key functionality of the UVM. For example, different baud rate, data length, parity enable, disable, 1 or 2 stop it. This environment is fully reusable and modular. We can easily extend it for more randomization, error injection, or coverage collection. So this completes the UVM verification in UVM section, where we combine system log and UVM to build a professional verification environment. In the next part, we will analyze the simulation output. Now let's run our code. Here in this we will see our result. Let the result to be built. Successfully compiled. And here we can see our result. So we are first reset our system for 5 times. So we can see for 5 times 1, 2, 3, 4, 5 times the system is reset. System resets in scoreboard. And then we are passing the transaction. The transaction that we are passing, that was rand81 without parity. It means random board with length 8. Let's see the result. We can see that random boards are generated for each iteration. We are iterating for 5 times and length is 8. In the data which is saved, the same data we receive in the RX data. The scoreboard will compare and it will say that our test pass or fail. So here our test is passed successfully in all the cases. So it completes our run part. Thank you everyone. Please like and subscribe to the channel. And if you have any query or questions, please comment in the comment section.